a warm welcome to everybody joining us on our Ekahau webinar series today. I'm really excited for the content because I know the team over at Extreme, Chris and Simon, have put together such fantastic content for you. We was going over it over the last couple of days and I was so engrossed and engaged at the content. I almost felt like I was on the webinar already. So I know there's lots of great stuff. There's a particular part that I find so fascinating about high density Wi-Fi that we're going to get to later in the show today. So why don't I pass it over to you, Stu, and you can do a quick round of formal introductions before we jump in.
Absolutely. Well, we've got Matt joining us here on the other side of the pond, and of course myself, Stu, or usually known as Sidekick Stu here, based out here today in Orlando. But most importantly, we got our speakers here today. We've got some first timers actually here, and we've got Chris Carr and Simon Vosper. So welcome, gents. I mean, this is your first webinar with us, and how are you guys doing?
Really well, really excited to be here.
Excellent, excellent. And Simon definitely was. It's also nice to see you on as well. And of course, we just saw Dale introduce himself on the back end. But it's great, guys. I'm really looking forward to the webinar here. And why don't we kick it off with that?
Perfect. All right. Well, I will stop sharing because I'm going to hand over to Chris and Simon to take it away.
And
thanks, Matt. Thanks, Stu.
There we go. That should be coming through okay.
Yep, all good.
Fantastic. Well, hello to all. It's great to be here. Great to have you all actually for this webinar here, where we're going to talk about high density Wi-Fi design. So the first piece we're going to cover was quite sobering. So who are we and what's our background? Well, my name is Chris Carr. I'm a principal solutions architect within Extreme, and my background is very much in Wi-Fi for the last 13 years. And I'm joined by my colleague, Simon. Simon, do you want to introduce yourself?
Yeah, hi, everybody. I'm Simon Vosper. So I've been with Extreme for about 9 years, but I too have a long history in the Wi-Fi industry, a little bit longer than Chris. Don't want to say how much longer, don't want to reveal too much about my age, but yeah, maybe the lion's share of that combined 30 years is my old age. But
still sobering though, right? Having combined 30 years, that was upsetting to put that on the slide, to be honest. But yeah, so here we are going to talk to you about high density Wi-Fi design. And what we intend to do first, before we even talk about it, is define what is it? What is high density Wi-Fi design? Well, I think it's not really definable by one person. So this is almost our get out of jail free card today, that if you put 300 people in a room that are Wi-Fi experts and you ask them to define and then deploy high density Wi-Fi, they're probably going to have different opinions. And funnily enough, Matt, I think we've got a day coming up with potentially even more than 300 Wi-Fi experts in the room, right?
Indeed, we do. So next week is our in-person conference happening in London, Wi-Fi Design Day. If you're in and around Europe and want to come along, please grab a ticket because we are very close to selling out. I just posted the link in the chat as well. If you want to come and join us and see us in person next week, please do so indeed. But yes, 300 or 400 of us Wi-Fi engineers in a room. What could possibly go wrong?
Right. And Simon and myself will be there as well. So if you want to argue any of the points that we do raise today, we'll try and avoid you, but we'll see what we can do. So what are we doing instead? Well, we're using our colleague and popular Wi-Fi guru, Mr. Coleman, and we're using his opinion today. So we're going to define Wi-Fi based on what David says, and ultimately you can argue with his book, which we are contractually obligated to try and sell as well because we work with David. So you are aware of the CWNA, you can absolutely have a look at this today. But let's go through those definitions then. So we define high density Wi-Fi as 3 different types of Wi-Fi. So we have high density, we have very high density, and we have ultra high density. Now this is a lot of text that I've stolen straight out of Dave's book, but it's a lot to read. So what we'll do instead is we'll summarize. Where do we see it? Well, we see high density Wi-Fi in open office spaces and things like classrooms. We start moving towards very high density when we look at large auditoriums, lecture theatres, any sort of function rooms that you may have, for example, in hospitality, in a hotel or something like that. And when we get to ultra high density, this is pretty much stadiums. This is the most difficult place to start deploying wireless. So that's what it is. Why is it? Why do we need high density? Well, I don't know what the opinion is of all the Wi-Fi engineers around the world, but certainly from what I've seen of all of my family and friends, this basic human needs pyramid doesn't really cover everything anymore, because there's something more fundamental that we need to have now, right? And we need to connect everything and anything you can possibly think of to the network. And how do we connect them is through the Wi-Fi. So whether it's our own personal devices, or even now as we start going into building management systems, as we need to have an IP address on every device we can feasibly think of within the infrastructure, within a building, we need to have this Wi-Fi there. So we really need to think about how much things are connecting to the wireless and how it is really a Wi-Fi first world out there now. So why are Simon and I speaking to you today? What do we want to try and give you from our experience and ultimately help you with? And really, the first thing is to help avoid pitfalls. I don't know about you, Simon, but I've had a few awkward mishaps, shall we say, throughout my ideas of trying to design high density Wi-Fi and even low density Wi-Fi at times.
Oh, yes.
Right? But we learn from our mistakes, and then we share them as well, so you can laugh at us and not make the same mistakes as well.
Yeah.
But there is a second part to this, is regardless of who you are, if you're a partner that sells Wi-Fi and consults on it, or if you're just a consultant that's just going through and doing these kind of surveys and helping consult on Wi-Fi deployments, or you're a customer, you're somebody that has purchased Wi-Fi and is looking to run it and deploy it and administer it, you need to have discussions with stakeholders at all levels and all technical levels. So you need to make sure you can have these communications with people who don't necessarily understand as much about Wi-Fi as we do here. So with that, let's start with the first kind of controversial thing that I would say is that Wi-Fi doesn't really make any sense, at least to normal people. It doesn't make sense. So what do I mean by that? Well, if I go through these, you might start being a bit concerned with some of these statements, right? Let's make every AP run on full power. Let's use as wide a channels as possible. Why wouldn't I want 320 megahertz? I want as much throughput as I can possibly get. Meshing things. What do you mean wires? Right? It's wireless, right? Well, sure, at home, I can just mesh these things together. And as we go through all of these different types of statement, my personal favorite, Simon, I don't know about you, but my favorite channel is channel 8. I don't know, do you have a different one that you would use?
That's cool, because mine's channel 7, so we can...
Oh, so we can, there you go, so we're not overlapping, right?
Yeah.
So the point that I'm kind of making here with this is, while these things seem silly, right, seem even frustrating to us at the moment as Wi-Fi engineers, where we go, why would you do that? Why would you pick these channels? Why would you turn... They're actually quite logical things to do when you don't understand how Wi-Fi works. Why wouldn't you want full power everywhere? Why wouldn't you want to pick channel 8? It's different to channel 6. It must be different, right? And so that's something we need to make sure that we put ourselves in the shoes of people who don't necessarily understand these details on the Wi-Fi side of things, and then try and explain why these are a problem. So what we're talking a lot about high density today. Let's identify why we think it's difficult. Why do we have to consider how to deploy high density? Well, we summarize it as two pieces. We summarize it as constraints and we summarize it as expectations, right? So what are the constraints placed on a Wi-Fi engineer? Well, first off, it might be a listed building or a special historical building where you can't just put access points where you need them. It could be a similar scenario, but for a different reason, aesthetics. There might be a specific way that we want an inside of a building to look. And we can't just mount the AP on the dinosaur here. We can't put it in the middle where we would want it. So we have to try and find somewhere else to put it. You might have a dodgy teacher that hasn't taught you right. I don't mean dodgy teacher, Matt, at all. I don't mean dodgy. I'm a fantastic teacher, but you might not have taken the courses yet. You might not have been on the ECSE.
Actually, why you say that, Chris? I think I found something that might be a bit more relevant. So I'm just going to see if I can just replace your can I only 1% can share at a time? Replace current share. Yeah, give me a second actually, because
He's grabbed it.
I think I
Uh-oh.
found something else. Maybe it's this guy that was the dodgy teacher.
I shouldn't have shared this with him beforehand, so he knew it was coming.
And I
Matt
mean,
wins.
That is
uh,
excellent.
oh, okay, but I mean, like, since we're in the UK, I kind of was curious, maybe he wasn't a teacher. What about if he was a wizard? So maybe in the next Harry Potter.
I mean, there's just dreams coming true, I think, here, right?
uh,
Oh dear.
Yeah,
You
there
set
we go.
yourself up there, Chris, I think.
No, I love it. There we
Yeah.
go. Can I have that wizard one after, please? I want to make that my wallpaper. And finally, on constraints, as we come back here, money as well, right? Sometimes we need to buy a number of APs, we need to buy access points, whatever it may be, but there are limitations on what we can actually achieve with that. The other side I mentioned was expectations. And so expectations can be incorrectly set by people who utilize typically the Wi-Fi at home, right? So they're utilizing the home Wi-Fi, you plug it in, you buy these wonderful meshing systems, everything just connects up, all the Wi-Fi works. And whilst, do not get me wrong, speed test is a wonderful tool and it's very useful for testing. It can also set some unrealistic expectations, right? That I don't know, Simon, how often are you designing to 400 plus megabit per client when we're doing high density?
I wish I could, but yeah, not too
Not
often.
quite got there yet, right?
No, the technology's not there.
Exactly. And actually, as an interesting side note on this is I once had this exact scenario where somebody did a test and they got a 40 meg throughput test. And when I informed them that, well, I designed to 5, so this is 8 times better than we designed it to, I think we're doing a pretty good job. That wasn't their expectation. So there was a real conversation that had to go on around that. So this is just to illustrate ultimately that we need to have expectations set with people who are typically going to be in senior roles that aren't necessarily understanding the Wi-Fi constraints underneath. Okay, so let's go through the first section then. So high density. So this is where we talked about offices and classrooms. So this is our office within the UK. This is Extreme's offices that we actually had the pleasure of hosting Matt not too long ago as he went through and surveyed our infrastructure. Fortunately, was mostly green there as well. And this is very much a high density deployment. So this is what we are looking to start the conversation with today. And let's see, why did we come to this kind of design? What considerations are there? And what we'll do is we'll quiz Simon because he's the high density expert around here.
Yikes.
So over to you, Simon.
Thank you, Chris. Yeah. So high density. So what we're talking about ultimately is maybe changing the way we design the networks, moving away from a coverage-based model and thinking more about how do we design for the capacity of the network, not just where can I get a good signal. So if we look back, 2015 is being quite kind. I can certainly remember designing Wi-Fi networks back a little bit further than that. What we would see is these coverage type models where what we'd look to do is try and cover a floor space. I mean, usually with as few APs as possible, right? Keep the costs down, but keep the design within some sort of limits. And those requirements or limits might be around RSSI, receive signal strength, or a signal to noise ratio. And then this was a nice way to do it because it helped keep that co-channel interference, that contention down. Because if we used as few APs as possible, we could use that 2.4 gigahertz channel model a lot easier. So what we would saw is these kind of coverage models. Today, what we might see in the same type of office environment would look kind of different. And that's because we're planning for capacity rather than just RF coverage. And to Chris's point and sort of how we define high density, you see it in office spaces now. What with a lot of companies going Wi-Fi first or Wi-Fi only in the office space, it's not uncommon to see these kind of high density type deployments, or certainly we would have called it high density once upon a time, being the norm. Okay, and we're doing this as a kind of normal procedure.
Yeah, absolutely. And actually, to throw this out to the chat as well, what is the most common like design that you see? Do you see people still asking for coverage more often, or do you see capacity? So if you drop in a note to say coverage or capacity, what are you seeing the most of now? Because certainly from my perspective and Simon's perspective, pretty much all we see is capacity now.
Yeah. But there's even still those RFPs that come through and they clearly define RSSI and signal strengths that they want us to adhere to for the network, but nothing else.
Yeah.
Right. So people have obviously gained enough knowledge to understand what the Wi-Fi requirements are, what the physical requirements for the Wi-Fi are, but not necessarily anything else. So, we still see RFPs coming through that are just asking for a signal strength, a signal to noise ratio everywhere.
Absolutely. And looking through it, obviously, and it depends, Chris, absolutely. But that being said, we're seeing a lot of people mention not just capacity, but even location services and things like that in there. So it's certainly not to say that there is no coverage requirements anymore, but the standards are more leaning towards capacity within that.
Yeah.
So Simon, your favorite question.
My favorite question.
Your favorite question. So how many devices can your AP support? How many do our AP support?
I'm trying to do the GIF,
face.
but you can't see my eyes rolling, right? Gosh, I hate this question. So the thing that you'll have seen from those two images we showed earlier is one of them has a lot more access points on it, right? So it's apparently obvious that when we talk about capacity, we're talking about more access points within a given area to fulfill the capacity requirements. Now, the question often comes up from people that don't necessarily understand is, how many concurrent devices do your AP support? Thinking about comparing it between different vendors or between different models. Another one that we see, and we've used extreme data sheets here, right? So we're not trying to get into vendor warfare. People look at the data sheets and they say, "Oh, I've checked your data sheet, and we see that you can support 1,500 devices on an access point, 512 devices per radio. So, for my 300 user office, one AP will be absolutely fine, right?"
Bit with spare, right?
Yeah, we've got a bit of headroom there as well. So, obviously, this is not correct. Now, this isn't the vendors trying to do you dirty and trying to sell you a lie. This is a real thing, right? There's only so many active associations we can have on a wireless interface, and we show that. But if your networks, if you're designing to these numbers, or you're even seeing that you're getting to these towards these numbers, you've done something terribly wrong. Yeah, and you're probably getting a lot of complaints about the Wi-Fi, okay? Because it's not about that. And what we have to do is change the mindset and change the focus from it being about the hardware, the infrastructure, the physical resources of the device that we're deploying being the factor that limits our capacity, and switch the focus onto the wireless medium, i.e. the frequency or the channel, and the channel access method. So how do we access that channel? How do we share that channel? And this is where we start to understand what our capacity is, right? So most people on the call will know. Some of you may not know, but Wi-Fi is like a contention-based medium, right? So everything that is using a particular wireless channel has to kind of take it in turns to send their data their data through. It's contention based. So we have to do our capacity forecasting around how that airtime, how each individual client gets access to the channel, and how that airtime consumption is kind of broken down. So we need to think about our airtime consumption. We need to think about the number of clients that we've got contending for the medium. And we also have to think about the capabilities of those clients, because not all clients are built equal, as we know, right? We have single stream devices, we have 2x2 kind of devices, we have different data rates that they support. And effectively, you know, what this affects is that client's efficiency with the airtime, how quickly they get on and off the air to transmit their data.
Maybe I can interject with a quick question here now.
Yeah.
So sometimes you see a data sheet for access points, and it will say that the access point is capable of doing, I don't know, the very top end one, 8x8x8, for example. But you've got a laptop there or a mobile device that's typically 2x2x2. So if you have a scenario where you've got a client device that's only a 2x2x2 but connects to an access point that can do 8x8x8 or 4x4x4, like what actually happens in that situation?
Really good question, and is commonly something that we get positioned as well, right? That we have a 2x2 access point. So when we then go, well, actually, we need more capacity in this area. So can we have your 4x4 access point in that area instead? But to your point, Matt, the 2x2 client is still only going to use two of those spatial streams, two of those antennas on the AP. There is some maths that you can do around it. There is some slightly better coverage and potentially slightly better data rates that you can get by having the extra antennas, but rarely does that translate into any significant performance increases, because ultimately there's just the highway as such where you've added 4 lanes. There's still only 2 of the lanes being used by those clients. So what we actually need to consider is, one, what is the capability of the medium as a whole? And what I say by that as well is, when people say, for example, well, multi-user MIMO, guys, that fixes this. In live environments, certainly our experience is not really. It doesn't. It needs 2 things. It needs spatial diversity, and it needs to be static clients. You don't really get that in high density. You don't get, 3 or 4 meters or yards of separation between things. So yeah, it's really when we position larger access points that are 4x4, for example, it's for other features that device may have. It would be that it has some capabilities to have a dedicated radio to do scanning for wireless intrusion prevention, or it might have some IoT radios in it as well. We very rarely are speccing them purely because of a perceived increased performance.
Yeah, I think we might push into this realms of where the 300 people don't always necessarily 100% agree here, right? And that it does matter, right? So the higher spec APs do have better resources, right? Better CPUs, better memory, things like that. So in terms of doing the modulation in that, they might be a little bit faster, and you might get some overall throughput gains from that as well, from having the better hardware. There might be some slight receive sensitivity gains from having the extra antennas. There are gains to be had, but they're very, very small. What we're trying to kind of get across here is, when we're doing the capacity forecasting, we don't really take those into consideration. The big things that we have to worry about is what are my client capabilities in terms of their data rates, and how are we chopping up the channel. So I would always advocate for buying the best hardware you can afford, because there will be gains to be had for that, for sure, but they're incremental, they're smaller on top of the actual proper capacity forecasting type of gains. Yeah. And just to finish off that kind of thought, really, the goal, what we're trying to do when we do this kind of capacity planning, forecasting and design, is what we want to do is increase efficient use of the spectrum that's available. So these are kind of like the meccas, right? This is what we want to get to. Decrease medium contention wherever possible, and RF interference. So be really efficient with the spectrum that we have, and take away as much medium contention and as much interference as we possibly can. Design it out. Yeah.
So
scripts.
The method then, how do we go about doing that?
The method, okay. So ultimately we have to, we need to start with the requirements, okay? We need to speak to our customers and find out what devices they're using, laptops, smartphones, you know, embedded devices, identify the data rates that they can support, you know, look at the actual throughput that they might be able to support. Obviously, the number of devices is really, really important. So try and sound out how many of each type of device that we're going to support. But the really important thing to think about as well is not necessarily the devices or the infrastructure, it's the applications that they're trying to support, because ultimately, if application works well, user happy, okay? They don't care about efficiency and about access point models and things like that. As long as their application's working, they are happy, right? So we need to understand, what does the application need to make user happy? And that's a very important part of the sort of capacity forecasting. So then we try and, oops, if we go just,
Oh, sorry.
because yeah, so what we do is we try and kind of forecast our capacity. We kind of try and work out how that airtime is going to be shared. Essentially, you know, each client device is going to get a slice of the pie. And what we try and do is work out, can we give each client a big enough slice of the pie to get enough throughput to make the application work, to make user happy? And there's a little illustration here on that just shows you how different devices might utilize their airtime. So, for example, for the same amount of throughput, a 2x2 or 2 spatial stream device is effectively twice as efficient with its airtime utilization as a 1 stream device, a single stream device. So we have to factor that in. You can go to the next one,
Yeah.
Chris. So I've gone a bit old school here, just to try and illustrate what we're talking about and how we would do this capacity forecasting. We put some maths on screen because everybody likes a big eye chart and to do a bit of maths in the afternoon, right? So put some assumptions in the corner, right? We're assuming we're on a 20 megahertz channel here, 29 dB. So all the clients are working at MCS rate 8, 256 QAM, 3/4 coding, right? So we need to kind of have a benchmark standard for the signal to noise and coverage that we're going to supply. So if we look at our single stream smartphone and our 2x2 laptop as examples, right? On the smartphone at those kind of data rates, 86.7 megabits per second. Now, actual device max TCP/IP throughput, we've done a 50% here, right? So it may be a little bit more than that in real world. You may see 60, more than 60% of the actual data rate. The reason that is so low is because there's a lot of overhead on Wi-Fi. So we need to actually understand what our real world TCP throughput is. And then we have a look at our target application throughput. So we find out, you know, what the application is that we're trying to support. In this instance, all we want to do is supply 1 megabits per second of real world TCP throughput to each of these client devices. So we can work out that one of these smartphones at that data rate requires 2.32% of the airtime to get enough data through 1 megabit per second throughput to make the application work, to make user happy. That's one device. We look at the laptop, we go through the similar sort of thing. Obviously, it's a much higher data rate. It's double roughly because it's a 2-stream device. The laptop only requires 1.13% airtime to get enough data through to make the application work. So when we do some forecasting, we actually add the device numbers in. Now we know that we want 100 of each device. Okay, so we can take that, take what we know about the airtime requirement for each device, multiply it out and get ourselves to a number of APs that we're going to need to support those devices. So if we times that 2.32% by 100, needs 232% of airtime. For the laptops, Again, 100 of those needs 113% of the airtime. Take those two figures and divide them by 80%, right? Because we wouldn't want to design our system to be running at 100% utilization. Doesn't really make sense. That means that gives us 2.9 for the smartphone, 1.4 for the laptop. If we add those together, assuming 100% concurrence, what we find is that we need 4.3 radios to give all of those devices enough airtime to get the required TCP throughput of 1 megabit per second. So we can translate that into 3 dual radio access points, right? That gives us 6 radios. And we've said that we need 4.3. We don't really do APs with a single radio. So 3 APs, 6 radios should cover us for those type of requirements. So what we've done here, obviously, I just wanted to show you the math to kind of show you, to help you understand how we do that capacity forecasting. Obviously, this is very old. I've been doing this for a little while, and this is how we used to do it when I were a lad.
That's a lot of math, though, right, Simon?
That's a lot of math.
That's a lot. I don't know about you guys, but my eyes are going blurry from all of that math.
It's a bit boring.
Wouldn't it be nicer if things can kind of do it for you, Matt?
Yes.
Indeed,
Right.
mate. I was just thinking, maybe I was wondering, have you been down the pub before coming to the webinar?
To get the courage up, absolutely. That's why I'm struck. That's why Simon did the math bit.
Yeah.
So what we suggest here is that we have tools available, and using capacity planners is also a great idea. So don't get me wrong, Simon's method obviously works, and if you're really into that, you can do it. But here now we've got tools in play that can help design around these requirements as well, that you can pop these numbers in.
But I think, Chris, is worth understanding how we get to those numbers, because sometimes we have to explain this to non-Wi-Fi people.
Yes, absolutely.
You know, if we can kind of just do, I mean, we call it on the back of a fag packet here in the UK. I don't know what everybody else calls it. Quick maths, you know.
Quick maths,
piece of paper, we can help someone that's non-Wi-Fi understand why we're going about it the way in which we're going about it. Yeah.
So on to channel interference management.
Yeah. So what we know is that, okay, we need a lot more APs when we do high density Wi-Fi. So we have to be a little bit careful about how we do our channel planning, because as we know, you know, any two devices that are using the same frequency or the same channel will contend for that channel, will contend for that frequency. So if you put two APs next to each other, all the clients and all the APs are actually in the same contention domain. They're contending for the same airtime. It doesn't really work. You haven't expanded your bandwidth. You've just put more devices sharing the same. So with that higher radio density, we have to be very careful about how we do our channel planning. So trying to separate the same channel by at least 2 cells if we possibly can. Separate adjacent channels by at least 1 cell if at all possible. I know sometimes it's hard, but the better we can get this, the more we can reduce the adjacent cell co-channel interference.
And Simon, are you an auto channel or a static channel kind of guy?
Ooh, good question. Ooh. Yeah. I'm going to kind of put a foot in both camps. I think in high density office type areas, things like that, I'm happy to go with the auto channel. I think that works quite well. In what we call the ultra uber super high density, you know, stadiums, things like that, we tend to stick to a fixed channel plan. You think about, we've got, you know, upwards of 600-700 access points in a big open space in a bowl. If you start to get 1 or 2 channel change events happening, that can have a huge domino effect. You see
cascade
APs
around, almost like a Mexican wave, right?
Can cause you massive problems. So maybe we'll talk a bit about on the testing and tuning that we do, but we go through quite a long process, well, not a long process, but a thorough process of testing and tuning in the stadium to make sure that we've got channel set right, power set right. We don't rely so much on the automatic channel stuff. Yeah.
Okay.
Reduce power if we can, and where we can, so that we're not creating huge amounts of noise, huge amounts of channel overlap, and always use 20 megahertz channels.
Well, funnily enough, I think we have a poll on this, don't we, Matt? So I'm in a slightly different and potentially putting myself at a bit of a risk here, a slightly different camp in this, and that is so. Simon thinks 20 megahertz only ever in every high density situation. And the main reason that Simon says that is because that when, for example, here we've got a capture from an 80 megahertz channel, it's inefficient to use wider channels because the primary channel ends up getting used for all of the management frames, whereas the rest of the channel then is kind of idle while the management frames are going on, which I absolutely agree with. However, my viewpoint, and this is going back to those different opinions that we mentioned at the start, which is still my get out of jail free card, is that while yes, that is absolutely true, in certain high density environments where there is less contention, so let's say you're not in the middle of a large city, and maybe you don't have the highest density in the office, you can get away with using 40 megahertz and you can utilize that. So I think, Matt, we have a poll to see whether anybody agrees with me or if I need to kind of check in my.
I'd like to add some weight to my argument as well, right? So
Please do while I'm voting.
let me explain. I would rather put 3 APs in, 2 APs in on 20 megahertz wide channels than 1 AP on a 40 megahertz wide channel. The big reason, well, 2 big reasons. One, as you said, Chris, the efficient use of the channel, but 2, you break up the contention domain. You actually split the APs between 2 channels rather than having them on one. Maybe a secret third working for a vendor. I get to sell more APs and go on more.
Absolutely. So I think we're going to let this play out, right, Matt, and see.
Oh, wicked. I can vote for myself. That's cool.
I'm just loving like the amount of like how fast the poll's going. Like people are answering. We're almost like 100% there we go.
Oh no, I can't.
Oh yeah, you guys can't see. Yeah, that's the
Damn, I thought I was going to get at least one vote.
Well, you see, Matt and I have wizardly powers behind the scenes, so
it seems.
Well, pretty much most of the audience have voted now, so I'm going to end the poll and then let me share the results. So I'm not too shocked about this. Most people seem to agree with you, Simon. I guess Chris is a bit of a dodgy looking geezer anyway,
I mean,
right? So
I can't argue with that. I haven't got my wizard hat on, right? But 25% of you, I must say, that's better than I was expecting.
Yeah.
I'll be able to buy you all a drink.
It's like you said right at the start, Chris, 300 Wi-Fi engineers in a room and you're probably going to get 300 different answers and
absolutely. And ultimately,
kind of evidence there.
We get to sell more access points. So there's kind of a win-win for me, regardless of which way it went. We're up to proper AP placement. I think this is the final piece on our high density section.
So, yeah, I mean, this is another one that probably plagues a lot of people designing and deploying Wi-Fi is being restricted on where they can put APs for whatever reason, because the architect doesn't want them there or because it's a listed building and things like this. So please try and do proper AP placement. Put the APs as close to the clients as you possibly can. Orientate them in the correct way. Now, I'm not saying they have to be horizontal. I'm not saying they have to be vertical, but do it in the way that you surveyed for. Do it in the way that is sensible, right, to get the best coverage and the best data rates for your clients. Try not to obstruct them. Yes, Wi-Fi is magic. It goes through things. It goes through walls. That's the beauty of it. But let's not make it go through things if it doesn't have to, right? Because it works better if it isn't. So try not to obstruct them. Put them behind silly things, that kind of stuff. Why? I mean, it sounds normal to us, but they work better when they're closer to the client. We can get more bits per cycle, per megahertz, right? Because higher data rates, better efficiency. The clients are more efficient with their use of the airtime. So that's why get them close, not obstructed and orientated in the correct way. This is going to make your clients and access points more efficient with their use of airtimes. And higher minimum basic data rates, please, for high density. Okay, try and remove those really, really low data rates. All of your management frames are sent at the lowest configured data rate. So, and that makes up a vast majority of the frames that are being sent on a wireless network. It's a lot of it is management frames. So if they're being sent at the slowest and lowest data rates, you're going to cause unnecessary congestion. So chop out the minimum basic data rates wherever you possibly can, or sorry, chop them, prune them up to higher data rates.
Perfect. So simple talk for normies, right? That's what we said at the start, was how do we translate this into conversations to have with people that aren't necessarily as technical? Home Wi-Fi and enterprise Wi-Fi aren't the same thing, so we can't compare them. We're not planning around 500 meg per client. I think I saw it in the chat as well that somebody mentioned the WAN link is always going to be a bottleneck within here. So when we talk about 46 gigabit speed on Wi-Fi 7, we're not talking about them. And even if we could achieve those kind of speeds, we're still going to hit these limits when we come to the WAN.
Yeah.
The capacity, stop thinking about just number of clients and start talking a bit about airtime. The best way I found to explain this to people who are less technical is to explain Wi-Fi as it's like a conversation and one device is talking at a time. So the more devices you add, the less efficient that gets. And we can't just expect these home numbers that we get when we're looking at an enterprise environment, and demonstrate it with some of the math if you think that that is going to go across and you want to go through Simon's explanation, or at least evidence it with tools like the Ekahau capacity planner there, where you can actually show what it's saying we need for a number of access points. Right, let's speed things along. That was the majority of the high density piece there. So now what you'll see in very high density, where we talked about auditoriums and function areas, guys, it's almost exactly the same. Right, it's the same considerations, just at a larger scale, where we need to think about potentially AP locations are a bit more considerations here as well, but we're going to cover a bit more on AP placements in ultra high density. But one thing that I want to pause and basically go on my soapbox here, because this is near and dear to my heart, because this has caused me many problems over my career. Let's talk about load balancing. So we haven't mentioned load balancing yet as a concept, and every vendor has some variation of load balancing. And we talk about it where we think logically, I want to spread the clients across the access points. Makes sense, right? Well, let's take this example. Let's zoom in on a few classrooms here. And let's say that we have some lovely extreme APs in these classrooms, and we've got 4 clients connected on the left classroom, we've got 33 in the middle because it's full, and we've got 9 on the right. Now, logically, if we wanted to balance those things across, we would start pushing them onto the adjacent access points, because that's what load balancing is trying to do. It sees that there are clients that could potentially be pushed onto less busy access points, so it'll try and push them over there. But that doesn't really work, because when you're in that classroom and you're under the AP and you're within capacity and it's working, then you don't want to move. The client doesn't want to move. It doesn't make sense. It particularly causes problems if there's any kind of roaming going along, because as you move down a corridor or around an office or whatever it may be, you're just going to get pushed onto different access points when you're trying to connect to the one that you think is the most logical to connect to, or at least your client does. And so in a classroom environment, this causes chaos. This just doesn't work. And I say this as I've seen it tens of times, if not hundreds of times now, where people think, and I understand why, let me enable that load balancing, let me start spreading the clients around and just break things all over the place. So that's not to say we never enable load balancing, but this is why we're talking about it in this very high density example, because in an auditorium, it does make sense. And load balancing absolutely can be something that we want to use. The problem we run into when we're looking at an auditorium like this, for example, is that when people coming through the door at the top of this floor plan, they connect to the closest access point and they stay there. They've got no reason to try and roam to another AP in the room, especially if you're using Omni antennas. And while we would recommend potentially considering looking at directional antennas in a situation like this, sometimes there are Omni ones used as well. So we need to consider how we push them into the room. There's no roaming requirement here because we're sitting down. And so ultimately, We just need a lot of radios, and we need to try and evenly spread people that are in the room over those radios. And so we do that with still our capacity calculations. We still use these low power settings. We still consider the kind of mounting positions and the antennas that we would use. But one thing to be very careful of depends on where your auditorium is. If you're doing load balancing within here and you're using omnis, then it's a good chance that if you're close to other areas as well, you can run into issues where clients are trying to go past the auditorium and they're not able to then have a successful roam, or they're connecting and getting pushed onto other APs. So we have to be very careful with very high density and with utilizing features like load balancing with that. So in very high density, the mounting matters. The aesthetics can be very important in these kinds of areas, but I can change aesthetics a lot easier than I can change physics. So we need to consider how we mount them. We need to consider the calculations that Simon has run through in even more numbers. And one key thing to consider when you are checking load balancing, just because you see an even number or a not even number of clients on the APs doesn't mean load balancing is working properly or it isn't working properly. So if you see 10 clients on AP1 and 40 clients on AP2, that's not a good measurement to say, well, that's not balancing, because those 10 clients might be utilizing way more airtime than the 40 that are maybe idle on the other access point. So we really need to consider, when you are measuring things like load balancing, don't just do the eye test and say how many associations are there. It's not an accurate way of understanding it. We need to assess the performance and look at the AP's airtime utilization ultimately to see if it is balancing correctly. And then to finish up, we get to the toughest area, right, Simon? The ultra high density. So
Yeah.
Let's have a look there.
Yeah. So what we're talking about really when we go into ultra high density is the stadium environment or the arena environment. Yeah. So you guys may or may not know that Extreme are kind of big in the arena, the sports arena part sector of the industry. So we partner with the NFL, Major League Baseball, NHL, all those guys. Obviously, we've done recently completed Old Trafford and deployments at Anfield. So what we're talking about when we mention ultra high density, kind of comes with some unique challenges. Design methodologies, I mean, largely it's the same, right? In terms of how we try and do forecast, capacity forecasting, right? It's the same technology, works the same way, do the same sort of thing, but obviously where we mount those access points and things like that, it becomes a little bit trickier. So you can see here some shots. Now these are all Extreme APs. We typically have two methods in the stadium for deployment. Now, strictly speaking, there is a third kind of hybrid of the two, but we just wanted to talk to you about the two main types. So left-hand side, we have overhead mounting, right, where we're going to shoot the signal down from an overhead position with a directed or a direct kind of beam of RF energy, right? So this is on the left-hand side, this is our stadium-specific access point, has software configurable radios, so we can actually choose the beam width that's coming out of that access point for different locations. On the right-hand side, you see the underseat mounting. Okay, so that is where we go around in the bowl, and we have a stadium-specific underseat access point that you're seeing there, and we put those right underneath people's feet. So there's reasons why we choose one over the other. Usually it's constraints. We prefer the underseat method. For an example, in the Premier League, there is a legal requirement on the gap between sort of stadium furniture and the stadium furniture in front of it. So in between those seats, there has to be a minimum gap. A lot of the stadiums that we deal with in the Premier League are, 100 years old, some of them, or in that region, and they just weren't designed to have the space to have an AP under there. So sometimes we're forced to do overhead type deployments. So kind of horses for courses.
But why do we prefer under seat, Simon?
Why do we prefer under seat? Excellent question, Chris. Well, we'll go through it with this lovely animated slide here. Okay, so Wi-Fi in your home, right? You have one access point, you have a device, and access point gives signal strength, signal to noise ratio, and you get a service, right? That this particular guy here, good signal strength, good signal to noise ratio, good service. We know that if you get closer to that access point, you get better service. You get a better signal to noise ratio, you get higher data rates, you get a better service. You move away, that service degrades, and then even further away to when you get a poor service. So we think about, we're mounting an access point, you know, right up in the gantries above someone's head, moving that AP right away from the user. The only way that we're going to make sure they get a half decent service is we have to turn the power up on that access point, right? So we have to beam a strong signal down to the user, which is all well and good. Now, when we add lots of users into the mix and access points on a very high transmit power, in fact, lots and lots of users and devices, ultra high density, and lots of access points, what we actually end up doing with all those access points on very high power beaming down from above is we're raising the noise floor. Okay, so yes, we may be able to give a good signal strength to the clients, but we've also got an incredibly highly elevated noise floor, which actually translates to a poor signal to noise ratio, poor wireless service. The answer, we move the clients closer to the access points. And that's what we do with the under seat design, as well as absorbing some of that RF energy and giving us a predictable cell size. So that's why it's kind of like a good, better, best approach. This is how we see it. Yes, we can do it with overhead. We would do it with under seat where possible, but we know that's not always possible, right? The construction requirements and, you know, like space requirements, it's not possible in every stadium. So sometimes we have to do things a little bit differently and do an overhead deployment.
How's that work?
So yeah, how does that work? Overhead access points, directional, kind of overlapping. We're aiming with the overhead model just because of you know, the side lobes of the directional access points, and how we fire them down, the distances at which we fire them down. The design modeling targets are around about 100 to 125 seats per access point. So when you're doing these ultra high density, it's really important to, as best you can, I know it's not easy, try and understand what the concurrency is going to be. How many people do you expect to actually connect to the wireless network? Just to give you an example, at Old Trafford, we see it topped out the last time we checked about 26,000 concurrently connected devices.
About a third of people that attend a match,
exactly right. Yeah,
typically.
so that's in a you know, 75,000 seater stadium, right? So we're looking at about 30%. Now this is, again, this is something that you have to understand and talk to your customer about. It differs in different sports, because our NFL stadiums, we see a slightly better uptake than that. We think perhaps why that is, you know, for some reason, you Americans like to take hours over a game of sport. So you're in the stadium for 3, 4, even more hours than that. People tend to get their phones out and connect to the Wi-Fi. With a football match, you're in, out, wham bam, thank you ma'am, 90 minutes, people don't get as much opportunity to connect. So maybe that's a contributing factor, but these are all things that we have to think about, right? What do we expect the uptake to be? Are we actually driving people to connect to the Wi-Fi? Are we incentivizing them to connect to the Wi-Fi? How's that going to impact our uptake?
So what's the drawback then when we look at overhead?
Yeah, so with overhead, obviously, you know, physical constraints. we're physically constrained in where we can mount access points. So we have done mounting to handrails, mounting to the rails around the pitch side rails, pointing back. Actually, we did that at Anfield, but obviously, you know, we are constrained by where we can physically put the access points. So what we've found is that the shorter distances are better. We can use the wider beam width on the directional stadium access point. Anything kind of up to sort of 30 feet, we can get a 230 megabits per second data rate, which, you know, with the targeted 100, 125 seats, 50% cell efficiency for a 2x2 device, some assumptions there, gives about 10 megabits per second of TCP/IP throughput per device. Contrast that if we have to stick the AP beyond that, you know, between 30 and 75 feet above the client, we get reduced data rates, and what that ultimately translates to is reduced throughput to the individual client. So it's not to say that we can't do it, but free space path loss is the primary signal factor here, and we're going to lose signal when we have to do it from further away.
So we can see a 10x performance increase just by bringing the AP that much closer.
Exactly right. Yeah. So it's pure physics, I'm afraid.
So then when we go for undersea.
Yeah. So undersea, and I will, you know, this tends to yield the best results from an RF environment, from a throughput to a device environment. Undersea design, this gives us a really predictable cell size. We aim for about 65 to 70 seats. So what we found is, for most stadiums, it does depend a slight variation on the width of the seat and the gap between the seats. In a row, it goes about 13 to 18 seats along, and then two or three rows back, 2 or 3 rows forward. The energy from the access point is contained by the people sat around it. So all of these big bags of water that come in to watch a game of football actually do a really nice job for us of containing that RF signal and stopping it from spilling out to the hundreds of other APs that we've got in the stadium, and to other APs that are sharing the channel. So what we found is we get much better performance, less CCI, less overall noise with this type of deployment. Yeah.
Fantastic. And then the last phase is the testing, and I've got a particularly flattering photo of me trying to do the testing. As a fun story, guys, I was told that I was going to go and do testing at one of the matches, and I would just be drinking beer and watching the game mostly and just running a few tests. Shortly then I ran into Simon, who went, "That's not what you're doing. You're going to run around for 90 minutes. More than half of the players were on the pitch at that point when I was watching Manchester United, and go through and do all of these test points." And that is me in, I think, the 85th minute, having finished my test points and ready to sleep for the next 3 days. I was I was not happy. I must say there were some choice words to the manager that had booked me in and sold me that particular story at that point. But really, I think,
so, you know, obviously we have to do some sort of rigorous testing with the stadium, and it's kind of difficult to do because when the stadium is full of people, the RF environment looks very different to when it's empty. So we have to do our testing during a game, which has its own challenges. Trying to pick through some angry football fans to take signal strength readings, throughput readings, can be quite a challenge. You know, obviously, mounting these APs in these, you know, way above and under the seat, you kind of have to get it right first time. There's not the same sort of scope for moving APs around as you might have in an office. So we test. We typically try and do, as I said, we don't tend to use automatic channel and power settings. So what we do is we'll do a series of test events at different games where we test, take the data back, go to the next game, make the changes, test again with those changes, bring the data back, go to a third game, test again before we hand it over. Yeah.
Fantastic. So guys, to summarize that last one for the UHD then. So underseat or overhead, which one do you guys think that is better based on Simon's preferences there? Don't compromise in that. We can't compromise in stadiums. So what we've been talking about before, there can be some compromises, there can be some inefficiencies. We can't in this kind of environment. And then to the end point, ultra high density is really hard. We have to test, then we have to go back and test some more, then we have to test again, and we have to use Ekahau and all sorts of other tools to go through this to make sure that we are able to provide this service at this level as well. So I'm conscious that we are running long here, so I just want to go into kind of the summary of what we wanted to cover in here. I'll just jump here. So one piece is just to say solid wired foundations are important. This isn't and was never going to be a webinar on going through all of those pieces, but just consider that power is able to be provided to the access points appropriately. Data plane centralization is absolutely something that needs to be considered, especially, for example, in the stadiums there where we get to that density. We typically want to centralize our data plane, but we also need to consider VLAN design, how we roam, if we're trying to avoid layer 3 roaming, which certainly I am whenever I can as well. Just make sure that we have the appropriate VLAN designed and we don't have these huge networks. So finishing this off, it's not about necessarily getting everything perfect. You have constraints on you. There are expectations that are placed upon you as well. So we need to make sure that we can compromise to an extent, but always provide a good enough design, and that good enough needs to be really defined. So always design to that requirement. So what Simon spoke about at the start, the maths, everything else around going through the capacity, ensure that those minimum expectations can be met and exceeded, because we need to consider the future as well. We can compromise. So there is some sensible compromise around AP placements and pieces in the high density and potentially even in very high density. But when we start getting to ultra high density, there's not even really sensible compromises that can go through at that point. And finally, it needs to be good enough for long enough. You can't just design to meet the absolute minimum spec that is okay now. What's going to be coming in the future? What are people going to be trying to design their Wi-Fi around? How are they going to be connecting things in 2 years, in 3 years, in 5 years? We're seeing an average lifespan of 7 to 9 years of Wi-Fi networks that people want to put in and keep in. So we need to at least consider 5 to 7 years in front to try and offer the service that is needed for that long.
I wanted to give the opportunity to the people on the webinar today to register for the next upcoming webinar, because we've got quite a lot of exciting things to announce. First of all, we will have a new host for you. A new member of the team is joining, so all will be revealed on the next Ekahau webinar. So to find out who that might be, you're going to want to register and come and see. Also, we have got lots of product news to keep you up to date on. So we've had quite a few features come out recently. You may be familiar with them, you might have missed them. I know it's quite difficult to keep up with these things, especially when they're coming out every couple of weeks. So we're going to do a bit of a recap of all of the new features that have come out over the last quarter. And then we're going to give you a bit of an insight and roadmap to a few new features that are going to be coming out in the next few months as well. So if you want to get signed up, find out what's been going on, see who's going to be the next Ekahau webinar host, then get yourselves signed up. Such amazing content. It is great to see so many people still here listening to these questions after the show. Chris, Simon, thank you so much for your time in putting together such a thoughtful breakdown of ultra high density, very high density, and high density different deployments and things you need to consider. Personally, I learned a lot. I found it fascinating hearing the different amounts of seats that you design for, depending if it's under seat or overhead, and lots of other great information. If you want to get yourself signed up for the next webinar, thank you, Jacob, for mentioning it again. If you're going to be in London next week at Wi-Fi Design Day, we look forward to seeing you there. You can come and say hi to Chris and Simon in person. Maybe you can tell them who you voted for on the poll, if it was Chris you agreed with, or if it was Simon. And we really look forward to having you there. So thank you, everybody, for joining us today. And Chris and Simon, again, thank you to you both for being here.
Thanks for having us.
Appreciate it.
Perfect. Well, see you guys in next week. Stu, Dale, and everybody else on the webinar. See you in 2 weeks' time on our next webinar.